Hi everyone, welcome to today's tutorial session. We will try and calculate or learn how to find the RMS value, that is the root mean squared value for the various waveforms. I have the sinusoidal waveform over here, I have the sawtooth waveform, and I have square waveforms over here. We'll try and find the RMS value. So after this video and you have any question, please place them in the comment section and I'll get back to you. Let's start. So we will start with finding the RMS value for this sine wave. The formula for finding the RMS value of a wave is this 1 over t integrating from 0 to t. Here will be your function squared t. So in this case we would have to find the function of this sine wave, square it and integrate from 0 to t. After that, we divide by the period of the whole cycle. We take the square root and then we will get the value for the RMS. So the function for a sine wave is equal to Vm sine omega t in this case. So Vm sine omega t in this case our function. So from the formula you can see that VRMS will be equal to the square root of 1 over t. In this case the period for this sine wave is from 0 to t, so t will be our period from 0 to t, and the function here is Vm sine omega t all squared dt. So VRMS will be equal to, so let's take off the square root and do all the computation, and then after that we will bring the square root back. So 1 over t integrating from 0 to t, squaring the function, we will have Vm squared sine omega t squared here dt. So then we can say that our VRMS will be equal to 1 over t integrating from 0 to t Vm squared sine squared omega t should all be in the bracket because that is the area of the cycle. But we realize that Vm squared over here is a constant, so we can bring it out. So Vm squared on t over here, and we'll integrate from 0 to t sine squared omega t dt. Integrating sine squared theta will be a bit complex, so we know that 2 sine squared omega t is equal to 1 minus cos 2 omega t. So if you want sine squared omega t, sine squared omega t will be equal to 1 minus cos 2 omega t or divided by 2. So then we can replace it or substitute. So our VRMS will be equal to Vm squared on t, from 0 to t, and here will be 1 minus cos 2 omega t all divided by 2 dt, like that. But 2 is a constant, this 2, so we can bring it out. So our VRMS equal to Vm squared, bringing the 2 out, we will have 2t here. We will integrate from 0 to t. We have 1 dt over here minus integrating from 0 to t cos 2 omega t dt, like that. So then our VRMS will be equal to Vm squared on 2t integrating 1 dt, or dt is the same as t t, but our limit is from 0 to t. And integrating cos 2 omega t, we will have sine 2 omega t all divided by omega t. And our limit is from 0 to t in this case. So continuing, our VRMS will be equal to Vm squared on 2t. Here will give us t minus, I can bring 1 minus 2 omega out, sine 2 omega, here will be t. But we know that omega is equal to 2 pi f, which is the same as 2 pi on t. That is, frequency is equal to 1 out of the period. So then we can fix this omega, or replace this omega with 2 pi t here. So let's see, V RMS will be equal to Vm squared all on 2t. Here will be t minus 1 over 2 omega here, sine 2. So we are replacing the omega with 2 pi on t. But we have this t over here. You see that this t will cancel this t. It will be left with just 2 pi. But we know that sine 2 times 2 times pi will give us 0. Sine 2 times pi is 0. So it means this part of the equation will be equal to 0. So then it will be left with just VRMS being equal to Vm squared all on 2t multiplying this t. So our final answer will be Vm squared t all over 2t. So VRMS will be equal to Vm squared t all over 2t. So you see that this t will cancel this t. We'll be left with Vm squared all on 2. But note that if you have this Vm squared on 2 and you multiply it by the period of the sine wave, you should get the area under the sine wave. But then if you want the RMS value, you will take just the square root of the Vm squared on 2, and then your final answer will be Vm all over root 2. So the next thing here is to try and find the RMS value for a sawtooth wave. Right. So we need to first find the function of the sawtooth wave, because we know that to find the RMS, we need the period of the cycle. You integrate 0 to t, you square the function like that, you can get your RMS value. What is the function of a sawtooth wave? Right, we can see that this is a straight line. We know that y is equal to mx plus c, where c is the intercept, or where this line cuts the y-axis. From the diagram, you can see that c is 0 because this line cuts the y-axis at 0, and x in this case will be t because we are dealing with time over here, as you can see. M is the gradient of the line, that is the change in y, the change in x, that is y2, y1 all over x2 minus x1. So at this point, we need coordinates of the line so that we can find the gradients. So let's say here is 0, 0. At this point, we can see that the coordinates is E and VM. If this is our x2 and this is our y2, we can say that the m equal to Vm minus 0 all over t minus 0. So our m is Vm t. Our function for this sawtooth is Vm on t times t. Then we can substitute VRMS equal to, so we will take the square root out, and when we are done, we fix it. 1 on t, because the period is from 0 to t, as you can see over here, 0 to t. We will integrate from 0 to t as usual. And then our function here is Vm all over this period times t all squared t. Then our V RMS equal to 1 over t, integrating from 0 to t. Squaring this function, we will get Vm squared all over t squared t squared t. So we know that Vm squared on t squared is constant, so we can bring it out so that it will multiply the 1 over t here. So our VRMS will be equal to Vm squared all over t cubed. That is t times t squared over here. You get t cubed. And then we will integrate from 0 to t squared dt over here. So then we can say that Vm squared all on t cubed integrating t squared equal to t cubed all on 3. The limit is from 0 to t. So VRMS will be equal to Vm squared all on t cubed times t cubed all on 3. So we can see that this t cube will cancel this one over here. So VRMS will be equal to Vm squared on 3. So the key thing here is that you should note that if you have your Vm squared on 3, the Vm squared in this case is your peak value, because you can see that from the diagram the Vm here is the peak value. So if you have your peak value, that's the Vm, and you square it all on 3 and you multiply it by the period of the sawtooth, you should get the area of the sawtooth. But if you want the RMS value, in this case, you will take the square root of the Vm squared on 3, and your final answer should be Vm all on root 3. Very simple. Yeah, so we will try and also find the RMS value for this rectangular, or let me say a square waveform. So VRMS in this case, square root 1 over the period of the cycle from 0 to t. Then we will square the function as we always do, dt. And this is the same as finding the area of the cycle and dividing by the period. So then we need to find the function of this cycle. Taking a look at this waveform, it looks like a piecewise function. So let's say the vt. We have positive side of the square waveform and the negative side of the squared waveform. So for the positive side, we can say that the function is Vm and it ranges from 0 to t on 2. And for the negative side, the function is minus Vm ranging from t on 2 to t. So the trick here is that, note, the function of a square or rectangular waveform is the same as the amplitude of the cycle. So in this case, the amplitude for the positive, let's say, squared is Vm. So you can see that the function I wrote Vm ranging from 0 to t on 2. And for the negative squared, that is this one, the function is negative Vm, as you can see over here, ranging from t on 2 to t. So I'm repeating that the function of a squared or a rectangular waveform is always equal to the amplitude. So now that we have the function of the positive side and the negative side of the cycle, because the cycle is from 0 to t, so that means it has a positive side and a negative side. So now we have the function over here, so then we can just fix it in the formula and go. So as usual, let's take off the square root and do the rest. When we are done, we bring back the square root. So for the positive side, we are integrating from 0 to t on 2, as you can see, and then we will square the function dt plus the negative side, that is from t on 2 to t, and we have minus Vm, and we will square it dt like that. So our VRMS here 1 on t, integrating from 0 to t on 2, we will have Vm squared over here dt, because Vm squared will give you this, right? So from t on 2 to t, we will have negative Vm squared is the same as Vm squared dt over here. Then we can see that VRMS will be equal to 1 on t. We can see that this Vm squared is a constant, so I can bring it out over here. So Vm squared 0 t on 2. So I'll have just dt over here. Plus, I know that this is also a constant, so I'll bring it out. Vm squared to be t on 2 t. Left with just dt like that. So let's continue. VRMS from here will be 1 on t Vm squared. When we integrate dt, we will have t, and the limit is from 0 to t on 2 plus Vm squared. Integrating the t again is t. The limit is from t on 2 to t, like that. So then VRMS will be equal to 1 on t Vm squared. Putting in the limit over here, I'll have t on 2 like that, plus Vm squared. So here will be t minus t on 2, like this. So then VRMS will be equal to 1 on t. Here will be Vm squared t all on 2 plus Vm squared times t minus Vm squared t all over 2. So you can see that this and this will cancel. So it will be left with just VRMS equal to 1 on t. And here will be just Vm squared times t. Simplifying this, we can see that Vm squared t all over t. So t will cancel t, and your VRMS will be equal to Vm squared. And again, note, if you want just the area of a square wave which looks like this, you just multiply this Vm squared times the period of that cycle, and this should give you the area under the square waveform. Alright, but if you want the RMS value, that is where you square the Vm squared, and your final answer will be just Vm, like that. This is very simple. Right, so interestingly, the last waveform that we will take a look at is also a square wave, but in this case you see that it has just the positive side and the other side lies on the x-axis. You can see that the cycle ranges from 0 to t, but from t on 2 to t will be 0. It will have no area because it lies on the x-axis like that. So our focus is to find the function of this square wave, and we are good to go. So from what we know, we are saying that if it is a square wave, the function is the same as the amplitude. So in this case, Vm, and it is ranging from 0 to t on 2, and from t on 2 to t, as I said earlier, ranging from t on 2 to t, like that. So VRMS, as we all know, is the square root of the 1 over period, integrate from 0 to t, and you square the function dt, which is always or equal to the area of the cycle, and you divide by the period of the cycle. So in this case, our VRMS, let's take off the square root, and after everything then we'll bring back the square root. So we'll integrate from 0 to t on 2 in this case, because t on 2 to t is 0. So now what is left for us is to integrate from 0 to t on 2 to get the area for this square wave. So the function is Vm to square it dt. So our VRMS will be equal to 1 on t, integrating from 0 to t on 2, we'll have Vm squared dt over here. And we know that Vm squared is a constant, right? So we can bring it out over here and integrate from 0 to t on 2 to be left with just dt over here. So we can say that VRMS will be equal to 1 on t Vm squared. So integrating the t, we will have t, and the limit is from 0 to t on 2 over here, like that. So VRMS will be equal to 1 on t. We have Vm squared over here. Putting in the limit, you have t on 2 like this. So it means that Vm squared is multiplying this. So let me write it here so that we can see it clearly. So I'll have Vm squared t on 2 over here, like that. So VRMS in this case will be 1 on t multiplying this. So I'll have Vm squared t all over 2t. So I'll see that T will cancel T. So RMS is Vm squared on 2. If you remember, when we were proving for the sine, we got that the VRMS was also equal to Vm squared on 2. So similarly, if you have a square waveform looking like this, and you want the area under that, let me say, square waveform, if you multiply the period by the Vm squared on 2, it should give you the area. And if you want the RMS value, you just take the square root of the Vm squared on 2, and you get Vm on root 2. So we can conclude that when your waveform looks like this, it is the same as the sinusoidal wave, because when we proved for the sine wave, we saw that our VRMS value was Vm on root 2. And for this also, we had Vm on root 2. So if you see this wave, it is the same as the sine wave. Thank you.